nonlinear optics, except with the important distinction that the Kerr coefficient of this thing is enhanced by the Q of the mechanical oscillator and the multiphoton cooperativity. So if you put the numbers, you would see that the Kerr coefficient here is about 10 to the 8 to 10 to the 9 times larger than that of any nonlinear crystal in any cavity. So that's sort of nice. So now you can go and measure these correlations.
This is for an optical system.
Right. But you could do this for a microwave system as well. So in John Teufel system, for example, this number is about factor 10 worse than ours. So you could get that. So there are quantum correlations between the phase and amplitude of the light coming out, and you can sort of measure it in one of two ways. I don't want to talk about this. Let me just go to the other. So which is the important thing is, if you have light that's in a coherent state and squeeze state as you come out, you can basically do homodyne detection with a rotated quadrature. And the idea is that the photocurrent that you have here is sort of a superposition of the amplitude and phase of the light that comes out. And the photocurrent spectrum now contains a part that has the correlation in it. And if you move to that quadrature where the correlation is sort of large and significant, you would actually see the photocurrent basically sort of dip below the ambient short noise level that you would expect. So this is exactly what squeezed light looks like. So we actually have a squeezing of about 1%. Since then we've actually improved this to about 10%, and that turns out to be limited by both our detection efficiency and the ratio of QBA to N thermal. But the point is that by shining light off of a reflecting mirror, you can actually make it non-classical. That's sort of the poetic way of putting it. Now the question becomes, well, all these experiments are sort of done in a cryogenic environment. I mean, LIGO really doesn't care about doing anything cryogenic. It's too much of a hassle. So can you actually do something on a room temperature experiment that might create something like squeezing? So we went back to the drawing board and sort of designed a slight variation on our system that sort of featured single photon cooperativity, which is about factor 2 to factor 2.5-ish larger. Part of that comes from using a larger cavity so that the optical quality is better. But then if you make a larger cavity, your sort of beam, most of the beam doesn't actually sample the cavity field, so that's sort of a dead mass. You sort of don't want that, so you kind of scallop some mass out, and then you just have an effective interaction region where most of the elastic energy is stored, and you can sort of have effective masses which are factors of few lower than what you would have if you did not scallop it. And with that sort of improvement, you can actually do a similar experiment, but now at room temperature, where you actually turn the quadrature. So you're just injecting standard coherent light, and you just change the measurement quadrature, and you can sort of see as you go from one quadrature to the other, symmetric across zero, you would see that some noise gets eaten out or cancelled. And it turns out that if you try to fit it to a model and try to understand what's going on, it's actually quantum noise getting coherently cancelled as you change the readout quadrature because of this interference between phase and amplitude in the output. And now you can ask, well, how is this useful, for example, do an improved measurement of a force? And it turns out the answer is yes. So what we did is to actually take say this mechanical oscillator and then apply say 2 radiation pressure forces using a second auxiliary laser and sort of balance them so that we are able to easily calibrate it, and then sort of try to make this measurement and make a measurement of the signal to noise ratio of the force as we change the measurement quadrature. And as we saw before, as you change the measurement quadrature, you sort of eat noise underneath this force via coherent quantum noise cancellation. And in fact, if you compare the signal to noise ratios of the two forces, you would actually see that it departs from say the classical value, which is this dashed line here, about unity, and you can actually get a few % improvement in the ability to estimate external forces. So that's sort of how quantum metrology happens, by simply making a more precise measurement of a mechanical oscillator. So you can cancel quantum noise in the measurement, and it's sort of complementary to injecting squeezed light in the interferometer. You're sort of generating squeezed light in the interferometer and then using it in situ to do back action cancellation. And that sort of is really helpful for LIGO, and that's how I actually came to LIGO. But before that, I'd just like to summarize this by saying, well, the sort of things that we've done on a tabletop sort of attacks 3 sort of frontiers. One is quantum technology, so we can generate things like squeezed light, precision measurements. So we've made the most precise measurement of a mechanical oscillator compared to its 0-point motion, and sort of fundamental physics where we observe things like quantum back action and the uncertainty principle on a sort of nano scale object. So now if you come to LIGO, why is all this useful for LIGO? Because LIGO is burdened by sensitivity. So this is the LIGO sensitivity plot, and sort of that is sort of pulled by this donkey or horse here, depending on who you ask, and that donkey is sort of eating quantum optics, research into coating thermal noise, Newtonian noise cancellation, make longer arms. These are sort of the low, easy to harder things in the long laundry list of things that you would do to improve the LIGO sensitivity curve. And this is sort of in line with how people see LIGO progressing over the next 5, 10, 20 years. So in quantum optics research in LIGO, 3 things have been considered so far. And sort of I've been involved in, the idea is that I'd be involved in all 3 things. So one is injection of phase and amplitude squeeze light to cancel quantum back action and short noise. The other is to inject squeeze light whose frequency dependence sort of changes from amplitude squeezed to phase squeezed as you go across the band, which has been demonstrated on a laboratory scale now, but being integrated into LIGO later next year. But also maybe the possibility of using this inherent Ponder motive correlations that exist when you make such a measurement, just by changing the readout angle. And in any case, if you want to do any of these things, there are 2 things, there are at least the 2 ways to attack this problem. The necessary requirement to doing any of this is to have balanced homodyne readout for LIGO, so that you can change quadratures and do the standard quantum optics. You have the standard quantum optics toolbox for measurement. The other is sort of if you want to make a squeeze light source, it has to satisfy sort of 3 broad conditions. One is that it has to be broadband at audio frequency, which is an enormous challenge. It has to be reasonably scalable, not cryogenic, and it has to be basically room temperature, so that things are easy.
Actually, I don't know much about this. Can you explain what you mean by broadband at audio frequency? Why audio frequency?
Oh, because this is audio frequency. So 10 hertz to 1 kilohertz is audio frequency. So what you want is squeezed short noise in the LIGO detection band, which is basically audio frequency offsets away from the optical carrier. So you can think of the 0 frequency here as being just the big optical carrier. And then once you have that picture in your mind, you sort of understand what the challenge is. You basically, on a LIGO laser, you want it to be short noise limited starting from 100 hertz away from the carrier, which is sort of an enormous and stupendous challenge. So I've basically been doing 2 sort of things to help LIGO in their quantum noise management plan. One is to basically design and implement a balanced homodyne detector. The other is to make a low frequency optomechanical squeezer. So I'll try to quickly go through at least one of them. So the low frequency optomechanical squeezer, so as I mentioned before, thermorefractive noise is what limits the performance of these optomechanical systems, optical optomechanical systems that we currently know. So one of the ideas is to not use amorphous materials which have large thermorefractive noise, but move to crystalline materials. And here we've chosen to use AlGas, which actually over the past few years has been shown to have thermorefractive noise properties which are sort of factors of 10 to 20 to maybe even 100 lower than conventional amorphous glass. So what we've done at MIT is basically design and develop a micro cantilever which has a crystalline mirror coating. And the mirror coating is sort of standard Bragg stack sort of thing, where we have alternating layers of galliards and AlGas over and over about 23 times, sort of designed to have a certain transmissivity, and that sort of forms our one end mirror, and the other end mirror is sort of just a fiber cavity. So you have a fiber, the fiber's face is straight cleaved, it's got a dimple made with a CO2 laser, and it's sort of coated with a standard Tantala stack, Tantala glass stack, which is sort of the standard thing. And then the transmissivities of these 2 end mirrors are matched in such a way that the thermorefractive properties of this sort of dominates, and that's already lower, basically because this is a highly transmissive mirror. And the entire system is operated in ultra high vacuum. And recently we've actually made some interesting measurements which are sort of very close to us having squeezed light from this sort of a setup at low frequency. So what you see here is basically the thermal noise measurement of such a device, a broadband thermal noise measurement. And what you would see is that the entire measurement is dominated by thermal noise of this, the fundamental mode of this end mirror. And one of the interesting things is if you make a broadband measurement such as this, you would actually start seeing differences between the various damping mechanisms that happen in such a cantilever. So there is this two models of damping, one of which is called viscous damping, which is sort of the standard thing that you have, and that sort of falls like 1 by f square. But then there is this other mechanism where you have internal damping, which is sort of got a slightly better frequency scaling as you go out in frequency. And why is that important? Because if you turn up the power in such a measurement, you can actually start seeing back action in this, and this is really fresh work. And you sort of see that if you partition the noise floor using a model, you would see that sort of in these frequency bands, you start seeing radiation pressure, quantum noise sort of start equaling or dominating over thermal noise. And if you do a calibrated measurement of the power in these noise power in these bands as a function of circulating power, you would actually see this sort of typical quantum back action scaling thing. So you actually observed quantum back action in the kilohertz regime for the first time. And in fact, we predict and we are soon sort of set to observe about 3 dB of optical squeezing when we have a homodyne measurement setup and sort of do the same old shebang.
Mechanical oscillator, the fundamental mode was now close to almost a kilohertz.
Right, so it's about a kilohertz.
The previous one was at
4 megahertz. Yeah. So that's a doubly clamped device. So this is singly clamped. So that's all. That already gives you something very soft. So yeah, so we are set to observe squeezing, which is sort of getting interesting for LIGO people. That's one of the things. The other thing is sort of we want to make a balanced homodyne readout for advanced LIGO's next upgrade called A+. And part of the reason why we want to do this is simply, well, one reason is because the current LIGO interferometer is not actually operated on resonance, which sort of spoils its sensitivity by a small amount. But if you had a balanced homodyne, you sort of can operate on resonance. And the reason why it's not operated on resonance is because for a technical reason, which I can get into later. The other reasons are sort of you can actually tune the readout quadrature, so you can harness these intrinsic correlations that exist. And then there are a bunch of technical improvements that you get from having a local oscillator picked up from somewhere else. And sort of this sort of exemplifies why you want to do that. So this black curve here is sort of the design sensitivity for advanced LIGO. The blue is what you observe. Well, why is there a gap? The gap is because you're not operating on resonance. More or less at these frequencies, that's the reason. Here, it's mostly limited by some excess noise. But at high frequency, at least, it's limited by the fact that we're not operating on resonance. And then for A+, with frequency dependent squeezing and balanced homodyne detection, we hope to achieve this red curve, which is sort of about 50 to 100 times better than what has been possible currently. So to quickly give you a flavor for the sort of challenges that one has when one works on a thing like LIGO, so let's take a look at the LIGO optics layout briefly. So there's the laser, there's a mirror here, it's called the power recycling cavity that sort of bounces light back into the interferometer. There are the two arms, and then light comes out here, and then there is some optical table here currently where measurements are, like the final photodetector sits and the measurements are actually made. So we want to basically pick off our homodyne local oscillator from somewhere here and then bring it to somewhere here to do balanced homodyne detection. And kind of the things that you face when you want to transport a beam of light from here to here, and that distance is about 30 meters, is things like, well, what is the phase noise stability that you have on the local oscillator as you transport it down? You want to suppress backscattering noise that can go into the interferometer and sort of spoil sensitivity. You want to design mode cleaning cavities here that would overlap and clean the local oscillator and the signal, and then make sure their overlap is perfect. And then how you do LO phase control. So to just give you a hint of the sort of challenges that doing optics on LIGO entails, I'll just talk about phase noise stability and just throw one plot at you, which is the following. So there's a 30-meter long optical path from this point to this point. And you can sort of ask yourself, well, how close to 30 meters should this optical path be before which you sort of spoil the sensitivity of the entire LIGO interferometer? It turns out that you need to keep that 30-meter long optical path to within 30 meters at the level of 10 to the minus 15 meter. So you need to keep an optical path stable to 30 meters to the size of an atom. That's what is required to make sure that LIGO sensitivity does not get spoiled. So how do you do that? Well, we've actually come up with various ways to do that, and kind of we are sort of settling down on using long triple stage mechanical pendulums, each with a resonance frequency of less than 1 hertz to hang our mirrors off and then bounce the mirrors off that to bring the light all the way down. And that sort of development is happening at MIT right now. So I guess that brings me to the end of my time, presumably. So I'll probably take 5 minutes to tell you, sort of what this means in the grand scheme of things for precision measurements and where at least my interests lie. So precision measurement is basically a vehicle for doing interesting science. So if you look at this plot, when measurement imprecision was at the level of the thermal motion, people sort of saw Brownian motion, measured it, and sort of that became the first proof of the atomic hypothesis. And Jean Perrin was given the Nobel Prize for doing that, and in fact inferring the Avogadro constant from that measurement. So when the imprecision sort of became close to the 0-point motion, people started doing ground state cooling and laser cooling and all that sort of thing. And we are in a new generation where the imprecision is sort of the square of the 0-point motion. So we can measure the motion of the oscillator with something like the square of its thermal noise, thermal occupation. And that is sort of the regime where you start seeing quantum back action and study measurement physics and sort of use quantum back action as a resource for metrology. So squeeze light, back action cancellation, and things like that. So we are in this place where when I started out, I said there's this possible discordance between quantum and macroscopic, but now we are sort of in this other regime where people are no longer surprised by this large, nanoscopic objects exhibiting quantum behavior. And the question is, what can you do? Where can you go from this sort of a regime? So one is you can just continue doing that sort of thing, but with interesting other devices. So to improve quantum metrology and do macroscopic tests of quantum mechanics and things like that. And the other is sort of go down. So try to follow this line even further down, and sort of things that I'm interested in is sort of do quantum measurements with precisions that are good enough to study relativistic limits of quantum measurement, which are sort of predicted in theory but are not acted upon by experiments, mostly because they're sort of hard to do. But now we sort of have a glimpse of maybe that's possible, and that sort of leads you into studying other effects like the Unruh effect, which is sort of like a non-inertial effect in quantum field theory. So these sort of become more tangible. So you can think of things like counter-motive squeezers for the third generation of LIGO, and you can think of how force sensing can be improved by using conditional squeeze states of motion.